Hi everyone, welcome back to my channel. Today we'll explore a powerful feature in the modern compilers, link time optimization or LTO. Basically, today's goal is that we'll look into at how it works, why it's important, and even go through a practical example to see LTO in action. So let's get started. So what is link time optimization? In large C and C++ projects, your program might be spread across multiple source files, and each file is compiled separately into an object file. When the linker combines all these object files into the final executable, LTO allows the compiler to optimize the program as a whole. And I think the major job of LTO can be many, but it can eliminate unused code, inline functions across file, as well as perform some dead code elimination or remove all the unused variable from the memory, etc. Just for a recap, so this is the C compilation process from this beautiful book called Practical Binary Analysis, and throughout our video basically series of the binary analysis we are following this. Just to give an overview of how compilation process look likes and where exactly linker comes into the picture. So this is the full design of the C compilation process, the 4 steps of C compilation process. It starts with multiple C files, and you all take the header files like has include, stdio, etc. Then C preprocessor expand those C files, include the headers, and then we have the compiler, which basically compiles the C file to the for the downstream assembler. Assembler takes those files and then generate object files, and then comes the linker into the picture. So basically the linker assembles all of these object files into one single binary executable, and the default name is a.out. So you can see one thing from here: compiler and linker works in a pipeline fashion. That means compiler doesn't know what kind of optimization or what kind of information the linker is going to update in the binary file. So because of that, compiler places all of this unnecessary information already in the object file, which should be removed, but compiler cannot do it because it is independent of the linker. But whenever you compile with this link time optimization flag or LTO, that means compiler knows what kind of optimization the linker is going to do, and based on that, it optimizes the each object file on its own. So that being said, now let's move on to one particular example we are going to see for the link time optimization. So for here, I have a very simple C program basically. I'll show that to you. So this C program is, as you can see, all it has is one global array of 5 elements, and then it has this structure Y, which is containing nothing but the pointer to the X variable. And then I instantiate this global structure with the my struct, and then where the pointer to X is basically pointing to X variable itself. And to make it interesting, I have this main function where I am not accessing any of the variable. So as per my understanding, with higher optimization, so this is intuitive that with higher optimization, the compiler will be able to know whether this global variables are accessed within the code or not. If not, it should remove it, right? But today we'll see how this kind of thing is cannot handled or optimized away by the compiler, because there is some symbolic references like pointer to X is initialized to X is done at the linking time, and that is why the compiler do not know whether to remove these variables or not. So again, to start, all we have here is basically this particular variable, and today we'll first see how the compiler reacts to it, and then we'll see how the initialization of X outside of the user code, that is the main code, is done by the linker. So for that, we'll come back to our shell, and what we'll do, we'll call the GCC, that is a famous compiler we'll use. With this -c flag, that means stop the GCC after the compilation, don't do the linking step. And then what you do is basically you put your C code name, and then you rename the object file as sample.o. Let's say this is sample1.o, and once you do that, so the compilation process has been completed, and now you have this sample1.o in your file. Now let's examine this sample1.o and how the global memory of the sample1.o looks like, and what kind of symbolic information we have in the sample1.o. Let's first look at the symbolic information we have in the sample 1.0. And what kind of symbolic information we are looking is basically there should be some information saying X should be assigned to pointer to X in the structure Y, something like that, because that kind of information compiler gives to the linker. Now, for to do that, what we'll do, we'll call this readelf function, and this kind of information is basically stored in the relocation section. So we'll just look into the relog section of the sample 1.0. So as I said previously also, you can see for this particular relocation data, there is this section called relocation.data.relog.local. And why this is in .data section? Because we already have an initialized variable, which is the structure X, and the initialized variables goes into the data section of the global memory. So global memory consists of three sections: data, RO data, as well as BSS, and the initialized variable goes to data. And that is why we have a relocation section symbol table for a local data in the data section. And you can see that this is the symbol which needs to be resolved, and it needs to be assigned to the pointer to X, right? One said that let's actually look like how this global memory section looks like. For this, today we'll use this tool called Ghidra, and basically we will first go into the location where the sample 1.0 is actually stored, and then what we will do, we'll just take it and drop it to Ghidra. Ghidra will automatically analyze it. It will say okay, and then you'll just drop it to this dragon symbol. That is where the Ghidra's GUI based disassembler exists. So it will open your binary, and it will ask you for static analysis it does, and recovering of function ID. So blah blah blah. We'll just ignore today and we'll do analyze. Our goal is to look into the data section. Again, coming back to the C file, in the data section, we have a global variable X as well as a structure myStruct, which is supposed to be initialized with X, right? But in the data section, before linking, all you can see is basically the X variable. Again, to show the correlation, X has this 5 element 10, 20, 30, 40, 50. And you can see 0A here, which is nothing but 10 and some padding after that. Then 14 is 20, and then 30, 40, 50. So all we can identify in the data section right now is the already initialized. Although we should have this my structure here, but the pointer to X equals to X hasn't been resolved yet, and that is why it's not in the data section. Currently, it is in this dot data dot relocation symbol for local data section. And you can see it knows that there is this my struct, and the relocation symbols of this X needs to be adjusted by the linker. Right. So this is how the binary look like before linking. Although everything should be present in the data section, but few things is all in the relocation sections for the linker to identify and link it. All right. Now you have observed an object file before the linking, and now we would like to do the linking also along with the compilation process. And for that, we'll call GCC with sample.o, and this is the default optimization. So I'll just say it's sample1 underscore o0, right? This is how this is the sample o is basically sample 1 dot 1.0 is basically, as you can say, is an ELF binary of 62-bit. It's not stripped and blah blah. It has other options like it is dynamically linked, and there is interpreter and some hash value. So all we can see sample 1.0 is basically an binary, not an object file. Now let's look at it, relocation symbols, and see whether same entries exist here or not. See here you can see in this relocations, basically it's a dynamic relocation section, and you cannot identify X anywhere in the symbolic name because the relocations or symbol resolve has been already done from this particular object file, and now there is no need to maintain that information in the binary file, and that is why we do not have it here. Now we saw that from the symbol table point of view, that relocation, that linking has been done by the linker. Now let's try to go into the Ghidra's GUI format and see how exactly the binary or the global structure looks like. So we have sample 1.0, we'll push it to Ghidra and we'll do the same thing. We'll open the GUI based disassembler view. It will ask you whether I want to analyze for all of these things or not. I'll just simply go with analyze. Now let's go back to the data section. So previously you can see we could only identify the X variable. Here also we have X variable 10, 20, 30, 40, 50, the hexadecimal code of the decimal values. Then we have some kind of padding to identify the difference between two things. And now you can see there is this my structure, which is supposed, and it should have a pointer to X, which is supposed to be the initial start address of the X, right? And you can see the initial start address now. It's 1010. So you can see this address 104010H, which is nothing but this 104010H. So the resolution of this particular variable within the my struct has been done by the linker, and that is why everything is present in the data section. Now, one key point to note is that, okay, we are saying, okay, maybe this is the default optimization, and that is why this variables, global variables, which are not actually used anywhere in the code, are still present in the global memory. Now, I want to show you why the other optimization or the higher optimization like O3 is not able to identify this particular things. And the reasons is basically the linker does the job and compiler doesn't know about what kind of resolution has been done by the linker, and that is why it cannot optimize this way. Just to show one example, let's recompile the same thing with the highest optimization, that is O3, and let's create a new binary O3 and let's analyze again by the Ghidra whether the particular variables are still there or not. Again, let's do the same thing. We'll drop it to Ghidra. We'll do basic analysis of the Ghidra. We'll open it in the Ghidra's GUI folder. Again, we'll give permission for all kind of analysis it wants to do. And now we have open for sample 103. See here now within the data section, you still have this variable called X and as well as the my structure. Now the question is, again, you might ask, it's not used, why it's there. It's just making the binary big enough and not efficient itself. Again, the point is there is a separation, linking and compilation process. If you really want it to be gone, what you are supposed to do is LTO, which basically gives compiler the information about what kind of linking resolution has been done, and based on that it prepares the binary itself. Let's call it sample 103 LTO. Once the compilation has been done, again let's redo the same step. We'll open Ghidra, we'll just drag and drop this LTO sample to Ghidra. It will ask you some prompts. We'll do that. We'll again open in Ghidra GUI format. It will ask you for all kind of in analysis. I will say yes. We'll analyze, and now let's go into the data section. Now you can see in the data section, apart from this extra data used by the compiler, we do not have the variable X also, as well as the global structure. Why? Because the linker optimization information is now present in the compiler, and the compiler is able to optimize the object file in such a way the underlying binary file is also optimized, right? So this is like just a simple example of what LTO can done, but link time optimization can do more than just remove unused variable. It can also inline function across translation units, eliminate dead code paths, and optimize memory access pattern. This optimization can actually significantly improve both performance as well as the binary size. So you may ask, where is LTO useful? It is particularly important in performance critical applications like video games, embedded systems, large scale softwares. Wherever you want an optimized performance, LTO can really help you out. However, obviously, if you include this LTO flag within your compilation, that means your compilation process is going to be going to take more time than its usual time. So it depends on the user requirement, what kind of repo it on to push, and based on that, you can either activate it or deactivate it. Again, to recap, link time optimization allows the compiler to perform whole program analysis and optimization at the linking stage. This can eliminate multiple things like unused code, inline function, optimize your program for both speed and size. Yeah, if you want to take your C or C++ project to the next level, do consider enabling LTO in your build process. Thanks for watching. If you found this video helpful, please like, share, and subscribe. Leave a comment below if you have any questions or suggestions for the future topics. See you for the next time. Thank you.